So did you post it first?
Yeah.
Okay. All right.
There's a notebook left after the review session. Is this anybody here?
1, 2, 1, 2, 3, 4, 5, 6, 7, 8. One. A little off. 139. Okay, it's 4:40, so we can start. Please log into if you want to participate. Please log on to piazza.com with your username and account, and then you should be able to see the first question that you also see here. So the way we do this is we look at the question, we think about it. You can discuss with your neighbors about like what you think. You know, when you are ready to go, you submit a vote. Right? We will wait a little bit until everybody thinks like, yeah, I think I got it. Right? Then we close that poll, and then we discuss the question a bit and move to the next one. All right? That's our little intro in every single lecture from now on. All right? So you should hopefully all have access to Piazza.com. And this morning we have figured out how to enable the TA to publish the post. And, you know, we did the same now. Hopefully it's the same question.
Yeah.
So it's perfectly fine to discuss. I know, then you come to an answer. It's just like for training, really here, learning experience. Maybe tell me how many
Okay, I didn't sign up for the wrong one.
No, but I don't. two students have problems. So who has problems logging in or whatnot? 3. Yay. 4 or 5. So sorry. It is just extra credit, so don't worry too much about it. Yeah. We can try to fix those after the lecture and over the time by resending emails and whatnot, right? I don't think we can fix it right now and figure out what your problem might be. Yeah, sorry. It's just, don't worry too much. It's just one lecture today. Extra credit won't account for an A plus or whatnot anyway, right? So this is mostly the learning experience to give everyone the possibility to learn. All right, so how are we doing? 88. So okay, please guys, I don't know how many people are in here. How many are online? 119, 88, 119. Oh, that's pretty good. So, okay, so there's still about 20 or 30 who can't make up their mind. Why don't you pick one? And then we count down from 10. Pick one. 10, 9. No pressure. 8. 7. Yeah, closer. 7, 6, 5, 4, 3, 2, 1. Close the poll. All right. Okay, because we have to close some. So now I want to discuss this. Any takers? Anyone who wants to give his answer, her answer?
Enzymes change the Gibbs free energy.
Okay. So we have one student saying that enzymes change the Gibbs free energy delta G. Maybe a quick poll, who likes the number D? That's one person. Yeah, exactly. Do you have a better one? Another one?
B, all enzymes catalyze chemical reactions.
That is correct. All enzymes catalyze chemical reactions. If there is more than one good answer, take the best one. That is also for midterms. Sometimes this can be confusing. Sometimes you think like, oh, I like B and C or whatever, right? Take the one you like better. So there will always be only one answer, right? Now, there are, of course, enzymes that are activated by allosteric modifiers, but not all enzymes. Right? There are enzymes that become more active when they are modified by phosphorylation, but not all enzymes. Actually, some enzymes get less active when phosphorylated. Enzymes never change the Gibbs free energy, ever, because that's physics, right? So enzymes don't change the laws, they can't do that, They can help with the transition state to lower the energy barrier, but they can't change Gibbs free energy delta G. Some enzymes must exclude water, but not all, right? So that's how it works. Let's go to the next one. All right, so again, look at that, think about it, discuss with your neighbors, friends, family. Here. So that's the idea. This morning we had a lot more discussion going on. So maybe that's very low energy here over the day. Class is exhausted. All right. How can a product of a chemical reaction become more energy rich than its corresponding substrate? Is that even possible? Yes. Can we just? Okay, I think we are good to close. Yay. Okay, so we're almost done. So 10, 9, 8, 8 and a half. Oh, I closed already. Okay. Can you reopen it again, please? Should be open now. Refresh or whatever. Just wait for me. So I want everybody to be happy. Right? It's not about anxiety, stress, or whatever, rushing, adrenaline. All right? So everybody can take a chance. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, close it. Okay, so any takers? A, B, C, D, or E? Oh, well, I went there, so now I go here. Yay. D. So we had AD. Any other opinions? There are other opinions.
A.
Why?
Because in order for the products to have a higher amount of energy than source you need to add in some form of energy, in this case work.
Yes. So that is correct. Now I do understand why students pick D, and the same happened this morning, of course. About like 65% has an A, and about 1/3 has D, or roughly, and some others pick randomly. And so the line of thought by B would be say, okay, so if I increase the randomness, I of course will alter the delta T, right? So so if I it would be more negative, right? So it's more spontaneous in a way. But that doesn't mean that the product actually will be at higher energy rate. So that's the line of thinking, but it's very clear work energy. So that is any type of work energy to become a product. So that was what I showed. This is uphill, moving an object uphill on the top of a mountain. You actually put in work. That's the idea. Very simple. So when I ask these questions, I usually try to be simple and straightforward. Yeah, unless it's really wrong. Okay. Third question. How can we make a chemical reaction perform faster?
is simple. Will to.
Okay, so 30 seconds. Make up your mind. All right, good discussions. Okay, 10, 9, 8. I still see some discussions. That's okay. You know, raise your hand. You say like, oh, we're very close, very close, very close. Are we good? 7, 8, 5. Did we put time here in the front? Oh, okay. So I was looking. Okay. 5, 4, 3, 2, 0. So I'll close it. All right. So how can we make a chemical reaction perform faster? Yes, please. E. Why that?
Because anything that would cause two things to bind more tightly would require more energy to break apart, and then so the reaction would go slower.
That is one way to argue. E is first of all correct. Yes. The answer, yeah, anything that would bind more, bind better. It's not always helpful, but it could be helpful. But the point is really when we lower the potential energy or reduce the potential energy, that is this transition state, that is the barrier that we have to overcome. If that's lower, more molecules will be able to make it over, right? So yeah, that would be faster overall. Okay. Yes?
I know that the last one is the right answer, but how would you negate by binding an inhibitor to an allosteric modifier?
Because first of all, inhibitor by the name inhibits a reaction. By that it means it's slower. Slower. I mean, inhibiting means like not so active. Just by the word. Let's see an agent. Let's exchange that word against like a compound, right? Instead of inhibitor. Now, even if there is a compound that would bind somewhere else, we don't know if that is the result of that would be making the enzyme faster or slower, right? There are allosteric modifiers that inhibit reactions, and yes, there are also allosteric modifiers that make it faster or better, right? Lower the energy, right? But that is not clear, and here it's actually saying an inhibitor, which is by the word slower. Yes.
Will you be able to view these questions after class?
We can post them. That's okay. No, no.
Thank you.
No problem. If I don't forget it, but yeah. There are. We just had this afternoon our, how do we call it, midterm prep session already. Maybe 30 students were there, perhaps 20 to 30 people. We went over similar things like over and over and over again until the students were laughing. It's like, oh yeah, we haven't done it already 10 times. So if you want to get more of these questions, download all the terms, right? We have, everything is published. There's many similar questions out there in different wording and so on. Yes?
Can you explain what an allosteric modifier is?
Yes, an allosteric modifier is a compound that binds to an enzyme at another site than the reactive catalytic site. So somewhere else, it's kind of Greek. Allo elsewhere, steric is the location, right? So that's, I had hoped I had said it before, but maybe I didn't. And then if it's then changed the protein conformation, then the enzyme might get more active or less active. Okay? Typical allosteric modifiers are, and we come to that later, for example, if you have a long pathway, the may be an allosteric modifier for the beginning of the pathway. So to make that slower, because the more product you have, the less null you want, right? So that is called feedback inhibition. That would be then a product of a pathway would inhibit its own formation. So otherwise it gets faster and faster and faster. It would work, right? So that would be one way of an allosteric modifier, but there are others. Yes.
So is the in this case with the potential energy the same as the activation?
Yes. Potential energy is like the status where you are on a delta G diagram. Yes.
Can you define transition state?
The transition state is the molecule at the most fragile state where it is on the top of the hill in the activation barrier, right? And it's uncomfortable, I often say. Some bonds are already stretched to the limit. They may break in the very next moment, right? Or some other molecule has attacked the reaction center, maybe a carbonyl, an amino group attacking a carbonyl, and it's about to make a new bond. That is the transition state. That is what needs to be stabilized. That is where the molecule is really high energy, stretching this and so on, really uncomfortable. All these other forces would say, no, we have a bond, we want to be close, right? So if you stretch it out, it's high potential energy. That's the top of the hill. Still not good. Any other better explanation that I just tried to give for the definition of a transition state? Yes, here's a definition of a transition state.
No, I don't know what that is. Adding water to it. Is kind of a chemical structure in between the product and the reaction.
Yeah, so that's what it is, right? So it's not really the substrate anymore, and it's not yet the product. Something is stretched to the limit. And anything that makes that situation better, more bearable, maybe by adding electrons, maybe by having a cation close, or maybe by excluding water better or so, that would lower that barrier and make the enzyme more active. Okay? Yeah. I don't have really there are examples in literature and so on. I don't have a figure for that here. All right, so let's one. What is acetyl-CoA? If you don't like an answer, don't answer. It's kind of always good. That sounds really bad. So we have 80% of the votes in. 30 seconds maybe, and then you decide, please. Ten, nine, eight, seven, six, five, four. Anyone need more time? 3, 2, 1. Okay. So let's close it. All right. And who has an opinion about this? Oh, there's an opinion.
Hello, I believe it's D.
Okay, we got D. Anyone in favor? Yes, it's D. Why?
According to this diagram over here, silicone wave inside the middle and creates that formula with other lipids, including triglycerides.
That is slide number 11. Yeah, so slide number 11, that is basically where acetyl-CoA was in the middle. It is a product, or when we say metabolism funnels into simple products, and acetyl-CoA would also be the starting block to make other things. And it's energy rich compared to acetate. All right. What is metabolism anyway? That should be fairly easy. I think. Oh, this? Yay. I'll just take the one that was in this, right? I copy pasted it. So the order is not the same like on the screen, but don't worry about it. Take whatever you have on your smartphone or. So, 88. And again, 88. That will never ask. Okay, out of 2. 10, 9, 8, 7, 6. Anyone need more time? 5, 4, 3, 2, 1, 0. Please close it. And again, somebody wants to discuss it. Somebody wants to discuss it. Maybe in here. Okay.
Conversion of chemicals within a cell.
Yep, very good. And you get extra credit if you send him an email. Okay. Yes, it's conversion of chemicals within a cell, and I think I made it a headline in some of the slides. I think, right? So, yeah. I don't I don't even think that any else is really competitive. True or false? Chemical reactions in the cell can only happen by active enzymes. True or false? So that's, the choice is easier. You get a 50% chance. They're not there. They're active. They are present. See, there's none of them. See, there's the active point. So there might be not the active enzymes that are there. So it had to happen or not. Okay, what's the verdict? Okay, so we have all the votes in, I think 10, 9, and so on. 2, 1, 0. Thank you. This was the quiz, and everybody is right. We had a 90 or something, 95% of the audience says no. Well, I guess you say no, right? Yes. So who wants to explain why there are chemical reactions in the cell that can happen without active enzymes? Who wants to explain that? Yes. There's many people. I've seen her first.
I think enzymes is like a catalyst. It's not like a reactant where you need it for a reaction.
Okay, so it's just a catalyst, so it can happen. Do you have any example of maybe something that may happen without an enzyme? CO2 too? Yes, that's true, especially in plants. That's absolutely true. So the formation of CO2 and bicarbonate into water. Somebody else, some other reaction that can happen? Any takers? Okay, think about a hydrolase. And hydrolases would cleave a product with water. Now, water itself may also do that, and we will see one enzyme that is there for a reaction that would also happen without that later on in the course, called gluconase or 6-phosphogluconase, where that would be a lactone would be cleaved by water, but the enzyme makes it faster. Right? So that's why evolution put an enzyme there. But even if the enzyme was not there, it would still happen. So hydrolases, hydrolysis may happen, but sometimes very slow. Others are oxidations. Oxidations may happen, right? Oxygen attacking a double bond. That could happen, right? Because double bonds can be oxidized, right? Could happen. So with oxygen around. So, but there might be enzymes that make it more specific or more or faster. So in principle, that's what enzymes do. They make things faster. Sometimes they make it so much faster that the reaction is actually measurable, right? I mean, yeah, so the activation barrier is so much lower than without the enzyme, it wouldn't happen at all, basically, right? But some reactions would happen if the reaction beer is not so high, would actually happen, but very slow. All right, good. So that's where we are with the course, and we can go on. That was half the time already. Wow. I think we have to make fewer questions next time. Which answers? We can answer. We can also put it online. Yes, with the correct ones. Okay, I will do that. That helps. Okay, so now let's look into the delta G differences. Difference in free energy, Gibbs free energy, for a given reaction. So if you have a reaction A to B, reversible to C and D, we can measure the concentrations of the compounds. And so if we do that and we look at the concentrations of C and D over the concentrations of A and B, take the logarithm, multiply by the temperature in Kelvin, multiply by minus R, R is the Avogadro's constant, that would give us the delta G difference. And what these apostrophe means, and the little zero there, this is at equilibrium under standard conditions. At equilibrium means we wait long enough so that there's as many molecules that make it from the right-hand side to the left-hand side, as well as molecules that make it from the left side to the right side. Equilibrium. Equilibrium does not mean nothing happens. It just means the same rate. Okay, back and forth. And under standard conditions, we will, look at that in a moment. What standard conditions in biochemistry means. That means these can be measured. The equilibrium constant K, we can abbreviate that as a constant K, because it's at equilibrium, constant, meaning it's not changing, and can put that in. So that's the way we can actually measure delta G or determine delta G. So here's an experiment where we do this, right? So we are in the laboratory. We take glucose 1-phosphate, which is a phosphorylated glucose. We take glucose 6-phosphate, which is also a phosphorylated glucose. We mix them together at pH 7 and 25 degrees Celsius. And we put an enzyme in between. This enzyme is here abbreviated as PGM. PGM stands for phosphoglucomutase. Many enzymes have good names, rational names. So if you hear an enzyme that says phosphogluco, that's usually the substrate. Sometimes it's the product, but in many cases it's the substrate. Phosphogluco means this enzyme will take phosphoglucose. Mutase is the type of enzyme it does. So a mutase is an enzyme that takes one type of a group, here a phosphate, from one position of the molecule to another position of the molecule. That's a mutase. So phosphoglucomutase basically takes a phosphate from the one position to the sixth position or the other way around. So then we wait a while and we measure, and we wait a little more and measure again, and we determine that we're at equilibrium. And at equilibrium, we measure then 2 millimoles of glucose 1-phosphate and 38 millimoles of glucose 6-phosphate. We put that into the equation. We said like glucose 6-phosphate over glucose 1-phosphate is 19, 38 by 2. We put that into K, get the logarithm, the natural logarithm, multiply by the temperature in Kelvin, 298, multiply by the gas constant, 8.315 joules per mole in Kelvin. So if we want to have it in kilojoules, make sure that you do the right conversions, right? So joules is not the same as kilojoules, by the way. Okay, if you do this all correctly, you come up with a negative 7.3 kilojoules per mole as the standard energy, delta Gibbs free energy. Okay, for this, you have actually determined it. You are maybe the first one who saw phosphoglucomutase and isolated the enzyme from somewhere. Okay, so that's what you do. And if you would do the drawing, you'd say, oh yeah, glucose 1-phosphate has higher potential energy than glucose 6-phosphate. At equilibrium, that's how it might look like roughly, but that does not mean glucose 1-phosphate would totally go away, right? It would only mean it's less. No? So at minus 7 kilojoules per mole. That's roughly it. So just becomes some flavor for it. Okay. So what does the biochemical standard reaction or standard condition actually mean? It's defined differently to physics. So in biochemistry, we define it as being at 25 degrees Celsius or 298 Kelvin, having 1 mole of all substrates and products, or 1 atmosphere if it's a gas, having pH 7, and having a lot of water. You know, that's a liter of water. 55.5 moles of water is like 1 liter. It's like your substrates are 1 mole and a lot of water, right? Which is actually not what cells are. Cells are much smaller than a liter, right? So you already know that by just looking at that these standard conditions are not the real conditions in the cell. So we will have to kind of like address that fact later, right? And then you might have some compounds that need magnesium or other salts, and we assume they're all there at those concentrations. So therefore, the real conditions are different. For example, in humans, we would have 37 degrees Celsius. In hot plants, it also might be 37. Right? Outside, perhaps. Okay, or cold. And then we have 310 Kelvin. More importantly, the initial concentration of substrates might be different, and the products might be different, right? So maybe you eat a burger or something else, you know? So then, of course, the initial concentrations of your molecules in your blood and in your cells will be different. So it's not equilibrium. So also, you might have products like carbon dioxide that might be removed out of the reaction center, so it's changing all the time, right? So it could be also true. So it would never become really at equilibrium. So that means delta G changes along the reaction. Whereas by definition, delta G0 never changes because that's under standard conditions, right? So we can now make an equation where we say the real delta G is of course also defined by RT ln, the real K versus the equilibrium K. We can separate these into ln K real minus RT ln K under equilibrium conditions. And we can also now reformulate it as being delta G is the standard delta G plus RT ln K. That means we can always measure the actual delta G if we know the equilibrium. So far, so clear? All right. So examples, I'll give these examples so that you have a feeling what K means in terms of delta G. All right. If we have as much product as substrate, that means that's 1, like as much product as substrate is 1. We put the 1 in, we will see that this would be the same as here, right? And therefore, the delta G is 0. So delta G 0 means not that nothing happens, but that just as much happens back and forth. That means also that if delta G is 0, it's always at equilibrium, right? So we would have as much product as substrate. If we have a very much negative delta G 0, let's say minus 17. Minus 17. That means we have 1,000-fold more product than substrate. So if we have 1,000 molecules, right? You know, almost all of them would go over to the right-hand side. It just doesn't mean that we have no substrate left. We have a little substrate left, but not much. Reversely, if we have positive delta G 17, right? It means almost no product is made. We have 1,000 molecules, and only 1 would become a product. Okay, so that's what it means. Just to get you an idea, right? So where we are, basically meaning if you have a delta G of 17 or 20 or that's a lot. You know, most of it is either making it or not making it. Right? If you have delta G of minus 11, we still have 100 to 1. So only 1% of the substrate would not be turned over. So it's very large delta G, or at least minus 11. And 99% of the reaction would go forward. Right? Make sense? Also, it means if we have minus 6, that's about 10. 10% might not make it. So minus 6, minus 10, minus 20 is really fairly large. But you see already that, if we have a negative 2, not much happening. So we still would have a lot of substrate left. If we have a positive 1, or positive 2, delta 2 kilojoules per mole, that would mean it's endergonic, it's not spontaneous, but that doesn't mean that no product is being made. Okay? So think about now a chain of reactions. A biochemical pathway is a chain of reactions. The first reaction would have a positive delta G of 1. Secondly, would have a positive delta G of 3. Third reaction would have a positive delta G of 2. Let's just assume that, right? And then the fourth reaction would have a negative delta G of minus 30. Yeah? So the last reaction would be so fast and so negative, it would pull all the other reactions forward. So delta G 1 plus 1 or 2 or 3 doesn't mean the reaction or the pathway cannot happen. It only means you need to have a very strong pull at the end. Okay, so minus 30 at the end might pull the train forward. Make sense? All right. So just to get you some idea. All right. So how do we really do this? How can we really go uphill? Here is the first reaction of glycolysis. We have glucose. We have phosphate. Maybe in the kitchen, we get phosphate from the pharmacy and glucose. Actually, or we have Coke. There's a lot of phosphate and not Diet Coke, but real Coke. We have a lot of glucose as well. Glucose, but it doesn't matter here. Okay, so we wait and wait and wait. Without the enzyme, nothing will happen. Okay. With the enzyme, now we put an enzyme in. This enzyme is called hexokinase. Hexo means Greek, means 6. Hexoses are all carbohydrates that have 6 carbons. So that's a hexosis. Glucose, for example, is a hexose, right? It has 6 carbons and it's a sugar. Kinase means it puts on a phosphate. So it's a good name for an enzyme. It says which substrates it would take. It takes hexoses. It not only takes glucose, but it also takes fructose, fruit sugar, apples, for example, or fructose. Would also take galactose, mannose, sorbose, allose, talose. There's a lot of sugars out there, right? Okay. So, but it would also take glucose, hexokinase. Now, if we look at that, it's plus 13.8 kilojoules per mole. So basically, kind of very, very few molecules would make it to the right-hand side. That's kind of, yeah, we can go uphill. But if that's all what happens, even with the enzyme hexokinase, not much would happen, right? You drink a meal, or you have a meal, a bit glucose-rich meal, a cake or so, right? So even if it's sucrose, the body would hydrolyze it into glucose and fructose. So a lot of sugar, and then you wait and wait and wait, and the sugar levels remain high. That's not how the cell operates, right? We need to have that first step a little faster. How can we go faster? The way we do this is if we have this 14 kilojoules per mole and we want to make it faster and more negative, we add or couple another reaction that has a much larger negative delta G. And this much larger reaction is hydrolysis of ATP, adenosine triphosphate, which is an adenosine with 3 phosphates on it. And we will look at the structure, not today, I guess. And this hydrolysis to ADP, meaning adenosine diphosphate, is very negative, has a negative delta G of minus 30. And now you understand minus 30 is a lot, is a lot. So So ATP is something that would really like to become ADP. Very fragile. Right? So if you couple that ATP to that reaction in hexokinase, then all of a sudden you just add it up. Like plus 14 minus 30 is minus 16. Right? Roundabout. So that means now all of a sudden this reaction becomes very much negative. We can also say we put work into that molecule, right? That's the same idea. We want to go uphill. We want to make an energy-rich compound. That was question number 1 today. We want to make it go uphill. We need to put work in, and this work is here in form of ATP or money. We have to pay for it. Invest. Also, people say it's an investment. Put money into your bank here. Okay, so that's the idea of using energy by coupling a positive reaction with a largely negative one. Now, in biochemistry, we would say glucose becomes glucose 6-phosphate, a little reaction arrow. We would even say it's pretty much unidirectional. It's not much, at minus 17, not many molecules that would make it backwards, right? Maybe, what did we say, 1 in 1,000 maybe? Was it right? I think so. Yeah. So not many. So with 99%. And then we don't even have the reversible arrow anymore. We'd say that's so much to one side lopsided, so that we say it's really going from the left-hand side to the right-hand side. And then we would add this ATP here, and this ATP is called a cofactor, because ATP is not only important in this reaction, ATP is important in many other reactions. We call it the cofactor. Not only for this enzyme, but for many other enzymes. Just like money, right? You can use it for many things. In fact, biochemists are lazy and sloppy. So often enough, they don't even put that in anymore. So you go to biochemical pathways, they would even say, yeah, just leave it out. We all know it's there, right? So often enough, we just say, hey, glucose to glucose 6-phosphate. Of course, it needs ATP for that because we know. All right, but the correct annotation would be, this way, ATP into ADP. All right, so that's how it can be done. Now, energy can also have different types of forms. So, for example, in physics, you can also have energy like in a battery. A lot of molecules or ions on one side and very few molecules on the other side. And that's the idea in biology when we put membranes, in there, and we separate organelles by membranes, so that we have maybe on one side a lot of molecules, and on this side not so many, right, of the same molecule. And that is also energy. It's also potential energy, right? And so this energy can be used if you have a transporter protein here, and this transporter protein would now transport this compound over here, for example, then you can use that energy. On the other hand, if you have very little of now this compound one here, very, very little, and you want to even increase the concentration here, you have to invest, right? You have to go uphill. You have to pump water uphill. And therefore you need to have ATP. These proteins, therefore, are called transporter proteins. And they're very, 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 very often ATP dependent, meaning they need ATP. So you take this energy here in this example, ATP, hydrolyze it to ADP. By that you can transport compounds from here to here, even if the concentration is here higher. Right? So that's the idea. So yes, it's the same type of energy, same type of delta G. You can use that delta G to make ATP as well, as we will see in a moment. So since this is delta G, there's an equation, right? And equations are fun. So this delta G is still RT ln, the concentration difference between side 2 and side 1. Now we have the charge of the ion. If it's a singly charged ion, let's say proton, that's one charge, so then it's 1. But if you have a doubly charged ion, say calcium, maybe you want to do calcium transport, your calcium channel or so. that would be charge would be 2. Mr. Faraday invented a constant. That's the Faraday constant, which just remains there for the rest of your life. Faraday constant is constant. And then the voltage difference. Now we have voltage differences in batteries, and we have a voltage difference in the cell as well. If you have a very good potentioset, you can measure the voltage difference, and so that gives you basically the delta G difference. Yeah? So you can calculate that. So you can also therefore now, of course, determine if a transport will be spontaneous or not spontaneous, just depending on, do I have higher concentration of that compound here or there? Okay? So that's because you can now put it into this equation here, and depending how your ratio or your K will look like, it will be either negative delta G or a positive delta G, meaning it's either spontaneous or not. Okay. That means this compartmentation allows storage of energy. If you put a lot of compounds, just like a reservoir in the Sierras, right? And can store a lot of potential energy, and then you can use that potential energy, and that is done actually in mitochondria. It's the powerhouse of the cell. So they store a lot of protons on one side of the membrane, and then they let it flow back, just like hydroelectric machine would do, right? The turbine, right? So let it flow back and use that potential energy difference to drive the formation of ATP. So that is what's happening in mitochondria. We will look into that after the second midterm, or after the first midterm at some point, in a little more detail. But that's how potential energy can be made into chemical energy. Okay. There's a third type of energy that is important for this course. This energy is the energy that relates to oxidation or reduction. So if you have a molecule that can be oxidized, you can say that it is a potential of being oxidized, or at the same point, its counterpart has a potential to be reduced. And as you know, the oxidation and reduction is the donating electrons or receiving electrons. So there's no reduction without oxidation of something else, and there's no oxidation without somebody receiving that electron. So therefore, we always look at redox pairs. Reduction and oxidation always goes in pairs. And for each reaction, if you just put in here an electron, no matter where it comes from, we can now look into that and define its redox potential by having the oxidized product always, or compound, always written on the left-hand side, and the reduced product always on the right-hand side. That is the nomenclature that people have agreed upon a long time ago, so that it's kind of systematic. So for example, here we have oxygen, and if oxygen gets 4 electrons and 4 protons for being neutral, then we have 2 water molecules. We see that the redox potential for this reaction would be 0.82 volts. And so we would put it up here. 0.82 is a positive number, multiplied by the number of electrons that are transferred, that is here 4, multiplied by 4, multiplied by the Faraday's constant, will give us a delta G of that reaction. So since this is a positive number, this is positive, that is a constant, that is negative, so therefore the delta G will be negative. Delta G negative means it will be spontaneous. So oxygen is a good oxidant. Oxygen likes to oxidize things. Oxygen likes to receive electrons. And in fact, oxygen is the ultimate electron acceptor in humans. That's why we breathe. That goes on in the mitochondria. Oxygen is going in there and waits for electrons to get these electrons and to be reduced to water. That's Okay? And you see now that's really a strong oxidant. Now, on the other hand, we can look at this one here, pyruvic acid, which is the product of glycolysis, can be reduced to lactic acid or lactate. If we put in the number here, minus 0.18, put it in here, multiply it by another negative factor, that means the total will be positive. That means, you know, we will have the reaction more on this side than on that side, right? Because it will be negative delta G. Positive delta G. You know, if you write it this way. That means this is not a good oxidation agent compared to oxygen, right? If we look here, right, it would be even more positive. So that means, you know, we would rather have more acetate than acetaldehyde. And here we would have rather water than oxygen. Okay, so this is how these so-called Nernst reactions or half reactions are written. And we can now combine these half reactions for an actual redox pair. So, for example, when we want to know, you know, can NADH reduce pyruvic acid to lactic acid? What would be the delta G? That would be a question, right? How much would we need? Would it even happen? Would it be spontaneous? So in order to do that, you would need the concentrations of the electron acceptor and the electron donor, get a logarithm, put the retention, the gas constant and the temperature divided by the number of electrons that are transferred, add the standard reduction potential, and get the actual one. So in order to make it easier, if you have it already given, it's just like the delta GE for a different for a given reaction is the actual redox potential of the oxidant minus the actual potential of the reductant. So there are several examples in the quizzes and in the exams. So pick some and test those out for yourself. But there's also many, many, many on the internet, of course. So just try that out. Look at like these kinds of questions if you can figure those out. And if you have a calculator, so a calculator will be allowed for midterm 1. All right? Always asking the question, is the following reaction possible or not possible? Will it go to the left-hand side? Will it go to the right-hand side? If I give you that, you know, and then of course we would always give you the temperature, we would always give you the gas constant, we will always give you the Faraday's constant, right? You will see that in exams. We will always give you the equations, so you don't have to memorize these equations, but you have to be able to put in the numbers in a correct form and understand what the question is all about. Okay? That may be harder than it looks like. Okay, so the summary of the first lecture. Free energies are additive. So yeah, we can have a coupled reaction and we can calculate delta G. Concentration differences across a membrane are also delta G. And redox reactions can be expressed at delta G by NF or minus NF delta E. So these are all delta G's and they're all exchangeable. So, you know, you can drive a chemical reaction by a concentration gradient. You know, on the other hand, you can also drive a transport reaction by a redox difference, right? So because these are all delta G's, and for physics, that's all what matters. Can it go to the left-hand side or not? All right, so now we start lecture 2, which is okay because we may be slower, and I don't think I will come even to the TCA cycle and before midterm 1. I'm pretty sure we won't be so fast. But that's fine. You know, slower means you actually have a chance to understand, hopefully, right? So, okay. Oxidation and reduction is something that makes many students nervous because it's always kind of hard to see electrons and see where they are and what they do and ugh, what is now the oxidant? What's now the react? And you never liked it even in high school, and now it comes and haunt you again. All right, so what it really means is you have here molecules. In this case, this is octane. Octane is, so again, Greek, 1, 2, 3, 4, 5, 6, 7, 8. Octane. Yeah? It's an alkane. Here we see it written in another way, and here it's written in the shorthand notation of chemists. Lots of carbons, lots of hydrogens, very high energy, very, very reduced molecule. We will look into that reduction in a second, very reduced. We put that into our car in a mixture, it's called gasoline, and not only octane, but like other things too. And then we add oxygen and ignition, and then we get an explosion, right? And that drives our car forward, right? Lots of little explosions, okay, in a very controlled manner. That's called driving. Very nice. So, but the motor will, in the exhaust you will have carbon dioxide and water produced if you have a very clean motor. And of course it gets hot, that's the first law of thermodynamics. No work without fun, okay? Or no work without heat. So that's the same thing happens in the cell, okay? The cell also loves to get, high energy molecules, right? High energy molecules. Here we see palmitic acid. Palmitic acid is a free fatty acid. Again, lots of carbons with lots of hydrogens, only that here on the one hand side it's already activated. There's a little group on it, carboxylic acid, because if nothing else hangs on to it, it's kind of hard for enzymes to deal with it. So it's always good to have some other moiety, we say in chemistry, something else hanging in. So this carboxylic acid would already activate these bonds here a little bit. Withdraw electrons. You may remember general chemistry. So we eat the fat, or in this case the fatty acid. We breathe. That means we can generate ATP in little explosions. These little explosions are not really explosions. They go in very, very tiny steps, one after the other. That is called the biochemical pathway. Okay, we will look into that in this course. Now, this is a very reduced molecule, lots of hydrogens per carbon. But there's other molecules that we can eat. We can eat a steak. We digest the proteins into amino acids. Then we look at here, the amino acid asparagine has some carbons with hydrogens on it, but also some carbons that already have nitrogens and oxygens on it. So this carbon has less energy compared to a hydrocarbon, compared to a fatty acid. But we can still get energy out of it by burning that. And so we can still run with an amino acids. And of course, we can do the same with sugars, right? So we look at the sugar here. There's glucose, carbons with oxygens on it, right? So less energetic than fat, but still with good fuel, right? We can still burn this, and that's called glycolysis. Burning glucose called glycolysis. Well, we hopefully start. We won't start at next lecture, but then after lecture 4, I think we will finally come to glycolysis. All right. So going back to what really does oxidation and reduction mean? Well, some people just count oxygens, and I did that for you right now. It's like, oh, look, there's lots of oxygens, there's lots of hydrogens. That is a simple way to look at things. If you have forgotten, if you get confused, if you have exam anxiety, then do that, right? If you are calm and good, you go to Wikipedia, and then you see that is a definition given at Wikipedia. What are oxidation states of the different atoms in my molecule, right? And this is depending on the electronegativities. So you compare the electronegativity of your atom and its adjacent neighbor. Here we do not have a periodic system of the elements. In the other room we have. So here, kind of good to know, carbon is in the 4th main group. Yeah? Things on the left-hand side, like hydrogen, is less electronegative. Hydrogen is in the 1st main group of the periodic system. I mean, you don't have lots of atoms to remember. Right? Carbon, 4th main group. So if we have now something that I do not have short here, this interesting experience on the back. So if you have now a carbon, see, that's why I don't go to the blackboard. So we have a carbon, we have a hydrogen onto it, another one, and another one, right? So the carbon, as I said, is now more electronegative. The rule said whoever is more electronegative gets all the electrons. All right? So if we do this for this molecule, carbon would get all the electrons. Each bond here is two electrons, so 2, 4, 6, 8. 8 electrons, right? 8 electrons. Carbon is in the fourth main group. 8 electrons, it has 8 electrons, fourth main group, meaning it's -4. It has too many electrons for its main group, so this is -4. All right? Make sense? Yeah? So now let's assume that this carbon has another carbon as a neighbor. And if we have two of the same atoms, they have the same electronegativity by definition. That's the definition here. So that means they share the bond. That means each of those gets 1 electron. 1 electron for this guy, 1 electron for this guy, and there's something else here. That means if we look at this carbon, it has now 2, 4, 6, 7 electrons. 7 electrons, it's still in the fourth main group, meaning that this one would be -3. Okay? That is what we see here at the end for this octane. This carbon has -3. See that? All right. So now let's have this guy also another carbon as a neighbor. Right? And again, this bond would be shared equally. Each of those would get 1 electron. Right? So then we count again for this carbon. 2, 4, 5, 6 electrons. 6 electrons, its carbon is still in the fourth main group, right? Meaning -2. So that's why these carbons all have -2, and this one has -3. That's all. It's not a real mystery. You can always look at that and say, oh, I understand that. Okay, so now let's look at this carbon. This carbon has 2 neighbors, both are oxygens. Oxygen is in the 6th main group of the periodic system. Oxygen is more electronegative. So oxygen here would get all the electrons. No electrons would remain at the carbon. 0. Carbon still in the fourth main group. So therefore it's missing 4 electrons. It's +4. So that is now +4. If I would ask you an exam, if we oxidize this carbon and get rid of the product as carbon dioxide, how many electrons are transferred? Your answer would be, that's very complicated mathematics. Okay, so how many electrons do we have from -2 to +4? 6, right? So that is the mathematics we do here. -2 + 4. So, 6 electrons, okay, right? So, and then if these electrons go, for example, into a molecule that carries 2, say NAD+ to NADH, NADH always carries 2 electrons, we would need 3 NAD+, that would receive the electrons. Okay, that is the idea of reduction and oxidation. If there is an element, you would have oxygen and oxygen nicely together. This is by definition 0, so the oxidation state here is 0 because there's 2 lone pairs, 2, 4, 5, 6. 6 electrons, oxygen is the 6th main group, oxidation state is 0, right? For water, it's always oxygen is more electronegative than the proton, so it would get both of these electrons there. 2, 4, 5, 6, 8. 8 electrons. Oxygen being in the 6th main group, therefore -2. The hydrogen here has no electron. It's in the first main group, therefore it's +1. All right, 4 minutes left. Jesus. All right. So I just want to say something here for you guys. Let's assume now, instead of putting octane into a tank, we put octane into a cell, and let's assume there is an enzyme that would take the octane and slowly oxidize it. Okay? Slowly oxidize means we would have a catalyst enzyme here. We would call it octane oxidase, you know, because the substrate and what it does, octane oxidase. This enzyme doesn't exist, just like virtual example. We now look at those and we say, well, this carbon now gets oxidized from -2 to -1, and then we get a double bond. You don't see oxygen here. That's kind of cool to see that we can have oxidations. You know, an oxidation means often a single bond going to a double bond. That's an oxidation, right? -2 to -1. Somebody else gets these electrons. This somebody else is half an oxygen, would become a water. Now, biochemists are weird. They do not follow logic all the time. So they would not call this usually, they would not call this oxidase, right? They would instead count hydrogens, right? So they would say, this molecule has now fewer hydrogens than this guy. So this has less hydrogens than before. And therefore, they call this less hydrogenase, okay? Right? That's how they call it. And so they call it less hydrogenase or dehydrogenase. So shortly DH. So this would be octane DH or octane dehydrogenase. Many enzymes in biochemistry are called dehydrogenase. And now you understand why they're called this way, right? Even if there's no hydrogen involved, by the way, just the mere fact of an oxidation they would call dehydrogenase. So we can play this game a little longer, you know, so we would have here a octane dehydrogenase. We get octene with a double bond. We have then the octene dehydrogenase. We get from -1 to 0 with a triple bond. Then we have the octene dehydrogenase. And in fact, now we have here maybe a hydroxyl group, right? So then this carbon becomes +1 with a double bond. Then we have another oxidation. Maybe we get a ketone here. A double ketone would not be very stable, by the way. So these are virtual examples, right? But you see the idea, like you can go from -2 to -1, 0, 0. And all of that would be called a pathway, an oxidation pathway, right? If these enzymes existed, right? And the alternative would be a reduction pathway or an anabolic pathway, you know, a reductase or a hydrogenase, right? Hydrogenase. Right? So that is the idea of pathways. This is how these pathways lead to oxidation reduction, how we can calculate electrons. And with that, I wish you a happy weekend, and we'll meet again on Tuesday.
During the coupled reactions, if there is like excess energies, are these energies going to be waste or?
No, this is an energy potential for delta G, which just tells you the relative energy state, whether or not it's gonna be spontaneous or not, whether or not the reaction will happen or not. It's not like energy that flows around, you know. So it's more like a ball rolling down from a hill. You know, it's like, well, before my ball had high energy, and afterwards not so much. And if I want to go up the hill, I have to put energy in. Right? That's the idea. Okay.
Just a quick question. Do we have to do oxidation state
Yes.
calculations? Okay.
That's why I explain it.
Oh, I have.
Okay. So for a couple of reactions,